All right, class, we're gonna get started. All right, so welcome back for the last time. So today's our last class. We'll be going over topics that could be on the final exam. So the main thing we're going to discuss today is I will ask you what could be on the final, and we'll go over those topics. Just a few reminders: the last homework and your CFD project are due tomorrow by 11:59 p.m. CFD project is a group assignment. Homework 11 is individual assignment, as they all have been. Any questions on that? Okay, as another reminder, final exam is on Monday, right? We drew the first exam of the entire scheduled exam period. So Monday morning, December 12th, 8 a.m. in this room will be the final exam. We're scheduled for 2 hours. So we have a bit more time than we did on any of the midterms. Any questions on that? Yeah, that's right.
Are you planning for the test to require the entire 2 hours, or should we be able to do it in class?
It'll likely require the entire 2 hours. I guess what would that change? So okay. I don't think you should be worried if you're getting it done super fast, but I expect for most people it'll take most of the time. I think typically students don't feel as rushed on the final as they do on the midterms. Yeah. You're welcome. Yeah. Will there be more questions? So it's not finished yet. Yeah, so it will be more than the midterm. Yeah. It's not going to be double the midterms in terms of number of questions. Yeah. Okay, what else? Yes, the question for Zoom and YouTube is, will there be separate questions about separate topics, or will it be mixed? So I do feel, so the exam is cumulative, right? In the sense that it will cover everything that we've done in this class. And that means I do expect you to be able to put together concepts from the beginning of the class with things that we've just learned in order to address a complete problem. I do try to guide you through that, right? So when I'm giving you A, B, C, D, E, or whatever, right? I'm trying to give you, so a lot of times if I give you a question that goes A, B, C, D, E, a lot of times what I really wanted to ask you was E, right? So as an example, the Great Salt Lake problem, what I really wanted to ask you all to do was to figure out what is the power requirement of taking an existing section of pipeline, adding in a section of water pipeline, and estimate what the power requirement is to stabilize the Great Salt Lake levels, right? That's the question I really want. I would ideally just ask you that one question, but that doesn't, that's a lot harder to do in an exam situation, right? Because you have to think about exactly how to set that up. So instead I broke it down, right, into first, what's the flow rate, right, to stabilize Great Salt Lake? Then what does that translate into flow velocity? Then what if we just assume it's all the same pipe? And then finally, what if we put in plastic water piping at the beginning? That's generally how I structure my questions. Yeah. Yeah, same policies. So the question was, is the final open note, open book? And the answer is yes, it's the same policies as it was for the midterms. Open notes, open class materials, open homeworks. You're not allowed to use the internet on the final, but otherwise open notes. Michael, you were next.
So you mentioned it was cumulative. Is there going to be an emphasis on the material we just covered, or is it going to be like relative?
Yes. So the question is on emphasis. Yeah, so the emphasis will be on material we've just covered. And I have released finals from 2019 and 2021 on Canvas that you can look at. I realized that I owe you solutions to the final from 2021. I have to clean those up and put them together, but that's now a top priority for me to get done. So you'll have the solutions as well, but you can then see what the emphasis was on there. Note that in 2019, we've discussed this before, but there is some difference in exactly what material was covered, and that is definitely reflected in the final. Yeah. Yeah, so for problems where you have to read the charts, for anything really you'd be talking about a pipe flow problem, right? Because that's the only time where we have iteration. So the question is about iteration. So the same kind of policy that I had for the midterm would apply, where I would only expect a single iteration, but I would expect you to tell me how you would finish the iteration. Okay. I will give you the charts. Yeah, I will give you the Moody chart, that table B1, table B2, and some property information. So similar to information that I've given you on previous exams, property and unit information. Let's just go. Yeah. The CD and CDA charts. Oh, so the question is, will you be given CDA charts on basic geometric shapes? I think what I will do is similar to what I told you I would do for minor losses is I'll give you the information or charts that you would need for a given problem. Yeah. Other questions? Yep. The textbook also has direct solutions. What do you mean direct solution? Oh, sorry. There's two types of iterations that we ran into in pipe problems. What are the two types of iterations that we ran into in solving pipe problems? So the first is a friction factor, right? Because the friction factor is defined implicitly. And that's not the iteration that I'm talking about. I do expect you to be able to find a value of friction factor, whether that's by iteratively solving the implicit form, by looking it up on the Moody chart is honestly the easiest, fastest way, and the way that I recommend you do on the exam, or by using something like the explicit forms for friction factor. So what's the other type of iteration that we ran into in pipe problems? So, yeah. Yes. So for example, the type 2 problems, so those I would not expect you to use. Yeah, if you state what you're using and what assumptions are behind it, then as long as it's appropriate, yeah, I would be okay with that. Yeah, so there are approximations for finding velocity. Yeah. Okay. Other questions, Alyssa? Yes. So the question is, we've talked a little bit about theory of CFD. Will that be on the exam? Yes. Theory and practice. So I expect, again, these are CFD is a group project. I expect everyone was involved in the group project. And so, for example, you see on 2021 exam, there were some questions about CFD that we discussed in class and should have been reinforced in the project. Same thing for Aspen, right? We had a lecture on Aspen. You had a homework on Aspen, right? A homework problem on Aspen. So, concepts on, I don't expect you all to be Aspen experts after doing one problem and having one lecture, right? But the basic concepts, right? Basically everything that we've covered in class, inclusive. Yeah, I mean, you're not going to be setting up an ANSYS fluent problem, right? Yeah. Yeah. Yeah, show me the results from what iteration or something. No. So the 2021 final, you'll see that there's a true false question about CFD, right? There's some questions about RANDs, I think, RANDs equations.
Just to clarify, open computer closed internet,
Yeah, so I do not expect you to be running CFD. I do not expect you to have CFD available to you, CFD solver available to you on the exam. But absolutely not. Yeah. Okay. What other questions? Yes, Trey.
If we have access to our computer, we run it using Excel for our iterations instead of
So can you use Excel for your iterations? If there's an iterative solution, I want you to show me how the iteration is working. Okay. Basically, and it's okay if you then use Excel, okay, but you need to explain to me how that Excel worked, right? And the easiest way to do that is to write out the iteration. Okay. Basically, so I know you can definitely have an Excel spreadsheet, right, that would solve a type 2 flow problem for you. But I want you to know how you would construct such a spreadsheet and show me that you know how to construct such a spreadsheet, if in that kind of question. Okay. Okay. What else? Yes.
More of a curiosity kind of question, but are the TAs going to be looking over the exam role and looking at it and see if they have any thoughts on it? Input on it?
So the question is, will the TAs be looking at the exam ahead of time? No, I don't typically do that for the final, just to make sure that the material is not out there in any form.
Okay.
Yeah. Other questions? Okay. All right. So my question for you all. Oh, just an update on the course evaluations. We're at 65%, so we're getting pretty close. So again, at 85%, I'll send out 2 hints for content on the midterm. And in years past, I've given like little bonus hints on other information that you may want to know, but that's not really about content of the midterm. Okay, so anything else before we get into topics? Okay. Well, we probably cry. It's not my goal to make you cry. It's not my goal to make you cry. So I hope not. I hope not. I hope not. Okay. So, all right. So my question to you all is, what could be on the exam? So final exam on Monday. What topics could be on the exam? Anyone want to start? Yeah. Bernoulli. Yeah. So going all the way back to, I'm going to write this under midterm 1 topics. Bernoulli. Right. Bernoulli could be on the exam. Yes, Trey. Capillary action. We covered it in class. It could be on the exam. I should clarify. I mean, one of the purposes in me doing this kind of topic review is to help you all brush up on topics that you may have forgotten about. I know we've covered a lot in this class, right? My intention here is not to overwhelm you or to try to make you cry. My intention here is to help you study, right? And so that if there's something that we're talking about here in class that you don't recognize, then make a note of that. Make sure you go back and review that before Monday. Everything that's on the exam will be discussed at the topic review, right? So everything that was on midterm 1 was discussed at the midterm 1 topic review. Everything that's going to be on the final will be discussed here. Okay, what else? Yeah. Sorry, what's that? Manometers, yeah. Okay, what else?
Any
Fluid statics. Yep. What else? Navier-Stokes. Yeah. So now we're into. Oh yeah, that's still. Yep. Navier-Stokes. Yeah, we covered a lot by midterm 1. So in general, this would be differential equations of fluid motion, right? Yep. Surface tension. So other things like a control volume form of balance equations. Right, so both of these would be, so we have mass, momentum, energy. Yep. So tensors. So the definition of viscosity and Newtonian fluid. I said when we were doing it that I don't expect you to know tensor calculus, but the Newtonian fluid tensor is defined in your text. We did discuss that in class, and we've used it in some of our derivations. So I don't expect you to be able to take the dot product of a tensor and a vector and all that thing. But the definition is something that I would expect you to know.
It's like definition of what a fluid is, and also what Newton's number.
Yeah. What is a fluid? What is a fluid? Just for you all. It's something that continuously deforms under shear. So examples of fluids: water. What else? Liquids, gases, right? Or fluid. Okay. So what is a fluid? Knudsen number. Right. The day one topic. What else? Yeah. The gradient operator. So yeah, the gradient operator, that's a vector operator. So yeah, so vector equations. Yep. So that comes into, we use the gradient operator in Navier-Stokes. We use the gradient operator in differential equation of mass balance. Yep. Velocity profiles. Yeah. Right. We just talked about a few. We really primarily talked about the shear profile and the pressure driven parabolic profile, but also turbulent flow profiles. Yep. Reynolds number. Yep. Let's give that its own board, but yes, definitely Reynolds number. Pi groups. Yeah. So now we're into midterm 2 topics. Pi groups, dimensionless numbers, the number and how to find these things, right? The number of pi groups and how to find them. What else? Yeah. Eulerian, yeah, Eulerian and Lagrangian coordinates. Yep. Right. Yeah. So the difference between those two. Yep. Yeah. Modeling, definitely. Right. That's definitely something that we've covered. So modeling problems where we have something at small scale and we are modeling it with something at larger scale. Saw that on midterm 2. Problem 2, C or D. What else? Yeah. Pipe flow. We could spend a month and a half on this, and we did, right? So pipe flow, right? We have the different types, 1 through 4, right? Problem types 1 through 4. What else do we have about pipe flow? Friction factor, series, parallel, right? Finding F, series, parallel, pump power. Yeah. Yeah, so finding working power from the pressure, right? We saw that on midterm 2. What else? Pipe design problems. Yeah, so design problems, that would be like, you mean like fine diameter? Yeah, that'd be like type 3. So airflow in a duct, if it's incompressible, is covered here, right? If it's compressible, that's chapter 9. Yeah, weird shape. Ducts that are non-circular. I'm not going to call them weird shape, but let's say they're non-circular. What else? Yeah. Reynolds averaging. So I'm going to write RANS. So Aspen does not do RANS. Aspen is not solving RANS. Aspen is solving doing basically the pipe flow type solutions like energy balance. CFD is solving the differential equations and it's typically using RANS. Although you can also do large eddy simulations in CFD, which we mentioned briefly in class. But for the most part, it's doing a RANS solution. Yep. What else? So we developed the RANS equations to deal with what? With what phenomenon that occurs at high Reynolds number? Turbulence. Yep. Yeah, so turbulence is another, so we developed the RANS equations to deal with turbulence, right? To deal with all of the eddies and complications that arise in turbulence. So turbulence and the RANS equations, and then Reynolds number for transition to turbulent flow. So what's the Reynolds number for transition to turbulent flow if we're dealing with a pipe? So we're now a little bit more nuanced than just saying it's above or below 2300. So what's the transitional regime in internal flow? Yeah, so we'd say about 10 to the third to 10 to the fourth. So what's stated in your book. That's a pretty good range, right? So about 1,000 to about 10,000. Over that range, we're in the transitional Reynolds number regime. This is that there be dragons range, right, on the Moody chart, where things get complicated and poorly defined. So about 10 to the third to 10 to the fourth for internal. What about for external flow? Not just 10. Yeah, so transitional RE is about what I've heard. Where does it start? 10 to the fifth to about 10 to the sixth. Okay. So external flow, we have transition 10 to the fifth, 10 to the sixth. Internal flow, somewhere 10 to the third, 10 to the fourth. So 2300 is in the middle of this range and is a reasonable cutoff to remember, right? Just to orient yourself. But in practice, if you're in this range, it's not like if you're at a Reynolds number of 2000, you're definitely laminar, right? If you're at a Reynolds number of 2000, you're decidedly in this transitional range. And we'd more properly say it spans this kind of range of Reynolds numbers. Okay, what else? Minor losses, yep. What else from anything else on pipe flow? Okay. So what about new topics? So we're in external flow. So what about external flow? What have we discussed in external flow? Boundary layers. What are the types of things that we discussed with boundary layers? Whether it separates or not. So boundary layers, we talked a little bit about separation and wake. right, for laminar and turbulent boundary layers. Stokes flow is something else. Yeah, Reynolds number much less than 1 is Stokes flow. So most of our discussion of laminar boundary layers was for a Reynolds number of up to 10 to the 5th. Okay, but that Stokes flow equation, which Rob covered in his lecture, is really only for Reynolds number less than or typically much less than 1.
Well, that's the thing, applies to like the separation, because the doesn't separate, right?
When we have Stokes flow, we don't even it's not even proper to really talk about a boundary layer in Stokes flow. We alluded to this a little bit, but in at Reynolds number, so remember the boundary layer. What's happening within the boundary layer? Like, how do we define the boundary layer? It's the region where something's important. Viscous effects, right? The boundary layer is the region where viscous effects are important. When we have Reynolds number much less than 1, then viscous effects are important over a huge distance away from the object. So there's really no boundary layer to speak of in that kind of flow. Yep. But yeah, important concept. It's where viscous effects are important. Okay, what else about boundary layers? Yeah. Mach number, yep, so compressible flow. And we'll go to compressible flow in a second. So compressible, it's okay with you. I'd like to go back to external flow for a second. Yep.
Just like which length to use,
Which length to use? Yeah, so which length do you use for Reynolds number? Which question to you all? Which length should you use for Reynolds number?
usually something parallel to the flow.
In external flow, usually something parallel to the flow, right? Right, we talked about how the big difference between this and this has to do with the fact that in external flow, we're measuring Reynolds number based on a dimension parallel to the flow. In internal flow, it's perpendicular. The length scale is perpendicular to the flow. Okay, what else from external flow and boundary layers? We have a lot on boundary layers, yeah. Yeah, so CD, CL, FD, we can write out our equation force of drag or lift, 1/2 rho C D or L times A times U squared, right? Which area to use? Right? How do we know what area to use for this thing? Not always what's wet by the fluid. So area would be often frontal area, right? So frontal area. It could be the wetted area, planform area. Now, it actually, you want to use the area for which you have that coefficient defined. Okay, but often for drag, it's going to be frontal area. Often for lift, it's going to be planform area. Right, so often drag. Okay. Yes. There's a blimp example in your text that I'm not sure if Rob went over in class, where the wetted area is used instead of the frontal or planform area. What's that? For a boat, yeah, for boat flow, it may be used. Wetted area may be used as well. Yep. All right, what else? External flows. So how about the, we talked about transition to turbulence. Right, we kind of tried, we mostly avoided this in an internal flow chapter, but we talked about it head on in the external flow chapter because it, if we have turbulent flow, in external flow, we had a transition from laminar to turbulent flow somewhere. So we cannot avoid it in external flow. We talked just conceptually, where does lift come from? Right, so just a little bit conceptually, where does lift come from? We know we can use, right, from Monday's lecture, we can use the things we've learned in this class to have some understanding of that. What else from external flow? Yeah.
Along a plane or something, you'll start off whatever, and then like turn to computer.
We talked about that for sure in this class. Transition to turbulence, and the fact that we do typically start out laminar, we have a transitional regime, and then we transition to turbulent flow downstream. So this means the boundary layer. So if we go to boundary layer, this would be like boundary layer thickness. So some things that we can do with that. All right, so our boundary layers, we have thickness for laminar versus turbulence flow, right? So we can define what the thickness is. We can define, we can use those expressions to find the drag force caused by the shear through the boundary layer. We have the velocity profiles. In laminar and turbulent boundary layer. We talked about flats, plates, coefficient of drag, which we developed from considering what happens on the boundary layer and considering what happens during that transition. And we talked, at least conceptually, about the boundary layer equations, which were a simplified form of the Navier-Stokes equations for boundary layer. We talked about, so other properties here would be like the thickness, delta, the momentum thickness, theta, displacement thickness, delta star, and our shape factor, H. We define these things for laminar and turbulent boundary layers. Right. Okay. And roughness, right? Is roughness important is surface roughness important in a laminar boundary layer? No. Is surface roughness important in a turbulent boundary layer? Yeah. Okay, anything else on external flow? Okay, let's talk about compressible. All right, so we had Mach number. What else about Mach number? What does Mach number tell us? Mach number tells us the velocity over the speed of sound, right? It's computed as velocity over the speed of sound. But now why do we bother computing this thing? What does it tell us? Whether we can assume incompressible. So I'm going to just say Mach number regimes, right? So for less than about 0.3, we say that it's incompressible, but we defined a number of different regimes based on the range of, based on what our Mach number was, right? Mach number of 1 was special. What is Mach number of 1? Choke flow if it's internal, okay? Mach number of 1, we'd call sonic. This is sonic. And this would be if internal. it would be choked. Okay. What else about compressible flow? Charts B1. Okay, what is chart B1? So the isentropic flow, right? Isentropic compressible flow of air as a perfect gas. Right, so there are a lot of assumptions that went into that. What is B2? Ratios of what? Across what? Normal shock waves, right? So this is normal shock waves. For what material? For air, right? Because it's for K, it's tabulated values of our normal shock relations for K is equal to 1.4. So K has to be 1.4, right? With a perfect gas for B1 and B2. What else from compressible flow? Yeah, so let's see, area changes in compressible in Mach number less than 1 versus Mach number greater than 1, right? And related to this and related to the sonic condition is choked flow. What's that? Yeah, and choked flow, and how M dot relationship for choked flow. What else from compressible flow? Yeah. Mach number relationship with pressure and density for isentropic flow, as well as for normal shocks, right? So these things essentially, these are tabulated Mach number relationships. So so we're saying pressure to atmosphere relationship, you mean for so like a duct exiting, right? So a duct exit, if we have converging versus converging diverging, right? Converging versus converging diverging. The plots that we showed or that we talked about what happens to pressure as we change the outlet pressure in these situations. So choking, the Mach wave angles, right? So angles of Mach waves in supersonic flow. The perfect gas, speed of sound, right? We developed and described an expression for speed of sound, basically the A in our Mach number, right? So if you know Mach number and you know temperature and K, like if you're in air and you have K of 1.4, then you can figure out the velocity in meters per second or something, right, from Mach number. Yep.
There were a bunch of reasons I was thinking about. Well, because the density is lower, higher than the atmosphere. I think that the speed is basically a plane going Mach 1. We go slower than.
Yeah, so the question is, because density does change as we move through the atmosphere, speed of sound absolutely changes as you move up in the atmosphere. So Mach 1 is not the same velocity in the upper atmosphere as it is at sea level. Absolutely. Yep. Other things from compressible flow. Yep. Yep, stagnation properties. Right, so you have T naught, P naught, rho naught. On related to stagnation properties would be A star. Right, so what is A star? The area at which the flow would become choked if it's accelerated or decelerated isentropically. Okay, so the area at which the flow would become Mach number 1 if accelerated or decelerated isentropically. Okay, but A star, yep. The actual area could everywhere be larger than A star. That's correct. Yeah, we can't get, yeah, something would have to change, right? In order for us to have an area lower than A star. What else? Okay. Yeah, so isentropic compressible flow of air. So with area changes. Oh, I also have compressible flow visualization and Schlieren just conceptually, right? We looked at a lot of Schlieren images of compressible flow. What does Schlieren show? Density, shows change in density, which allows us to visualize where compressible flow is. We talked about this a bit during class when we started looking at those visualizations, and also during the videos going over how this works, and that's really more of a conceptual thing. Okay, so what about CFD? What have we done for CFD? Rand's equations. CFD, so Rand's and we talked very briefly about turbulence modeling. But just the concept that we need to do turbulence modeling of some kind with the Rand's equations. What else did we talk about for CFD? Mesh, yeah. So size, mesh independence. Something that many of you are probably considering right now for the final project. What else for CFD? Boundary conditions, yep. Boundary conditions for CFD. Numerical convergence. Numerical convergence. Versus mesh independence. Right, they're not the same thing. What else? So we spent a lot of time talking about decisions you make when you're setting up the CFD, right? I'm gonna write it as decisions. So we make a lot of decisions when we're setting up the CFD. Some of these are physics-based and should impact your solution, right? Like the choice of viscosity, or the boundary conditions, or the exact set of equations that you use, and so on. Some of these are arbitrary and should not affect your solution, like the mesh size or exactly which turbulence model you use, and so on, right? So we talked about decisions you make when setting up CFD as a kind of general framework for understanding what's going on in a CFD solution. All right, what else? Anything else? We covered my list. Yeah. Does anyone have any other ideas that I could ask? Okay. Yeah. Yep.
I guess there's our assignments that you gave us, and then there's exercises that are going to site. You need to them or just enough.
So some of not every project, some of this, and this is something that changed this year, and that I was talking with one of your classmates about. There are now some exercises associated with some of the assignments have exercises where you go like well beyond the initial solution. I don't expect you to do the exercises portion. If your assignment has that exercises portion at the end. Yeah.
Have the model, look at it, make sure it like makes sense numerically, and then where additional thing you want to do is
If there, so I will say, if there is a section that says that is titled exercises, that I don't expect you to be doing. Everything ahead of that, I expect you to be doing. Any other questions, comments? Yes, Jenna. So if the flow is supersonic everywhere and bigger than A star, can you assume it was choked previously? If it, practically speaking, yes. Yeah, it had to have come from somewhere. Yep. Any other questions? All right, thank you all. It's been a fun semester. Thank you for bearing with me over the past week of uncertainty and so on as well. I'll see you all on Monday. Yeah, and if I don't see you, I don't have another chance. Have a great break afterwards. Okay. Thank you again.